So today we are going to talk about types, and it will not be a general discussion about types. It will be constraints to domain-driven design, because as you already know, domain-driven design had a significant influence in how we have built and developed software in the last at least decade, if not more. We even saw in the previous presentation that it's good to think about the domain when we try to model our data, when we try to decide how we are going to organize the data, right? So what we are going to do today is to share the experience we had in applying domain-driven design for building .NET applications. And in order to do that, we have looked to see how we can make use of the types and the type system in every language, programming language that we have, in order to be able to model domain-driven design concepts into our programs. So before we dive into some examples today, I want us to have a look first to see what a type system is. And a type system is actually a logical system that allows us to attach a property called type to elements of a program, such as variables or functions. And the main reason why we want to do that is to give meaning to our programs, to make them resonate, to make them be self-explained, self-documented programs. And this is quite in line with domain-driven design, because in domain-driven design we want to build domain semantic into the program. So kind of makes sense that when you try to apply domain-driven design, you want to think about what types do I need in order to be able to build programs that are much more expressive. So there are many things and many benefits of using types in a program. Among some of them, we have early feedback. So we use compile time checks in order to see when there is something wrong in the structure of the program we have created. We use autocomplete in order to prevent things from going wrong, to anticipate and tell the developer what options there are, so that it can first build a correct program instead of having to protect from in order to correct it after it has failed. We also use classes in C#, for example, to break the code into smaller parts, so that it's easier to manage the complexity of the program. And more importantly, we are using types to make programs self-documented. We want to make intent clear. We want to model domain constraints into our programs. And more importantly, we want to limit the options for creating invalid programs. And this is what we want to talk today about, how we can restrict and how we can make sure that in the first place, the chances for us to build incorrect programs from domain point of view are small. That being said, I'm going to hand over now to Fedo to show you some examples inspired from the domain of an invoicing application, which is one of the many domains we have to model at Access. Fedo?
Yeah, thank you. So I will start with how I would model the invoice using C# and .NET, and that's why I asked how many of you are familiar with this. But it's not necessarily important the language that we use, it's how we use it. So if I would be a regular developer, I would just write the invoice class that would have some properties like customer details, when the invoice is created, when it needs to be paid, maybe some payment details, the invoice lines, the invoice total, and so on. So that looks fairly okay, right? But let's think about how many things can go wrong, as Danny said. So creation date and due date from a business domain, there is some constraints that we need to have. Like you can have a due date before the creation date, right? And then the payments, like you cannot have a payment detail if the status of the invoice is invalid, right? Or the payment date needs to be after the creation date, and so on. So there's all sorts of business domains that this model doesn't encapsulate and allows us to create invalid entities or entities with an invalid state. And then again, the totals, we have business rules where the gross needs to be the sum of the tax and net. Look at the decimal, which is the system type. Is that enough to represent amounts in C#? And how do we represent currency for the invoice? So that's just a brief, let's say, overview, because I haven't gone into the details of the customer or the payment details of the invoice line and so on. I just wanted to scrap a little bit to explain that there are so many things that can go wrong by just using a simple, the system types and the simple model. And we've talked a lot about illegal states. So this is the focus for the next couple of slides, is how can we make illegal state unrepresentable in our program. So what is an illegal state, or how can we get into an illegal state? There are several ways. We can call functions with the incorrect parameters, like passing in the username instead of a user email address, allowing constructing objects with data that doesn't follow our business rules, or calling functions with data that is erroneous when the function expects valid data. And then the last 2 points are around transitioning, like the invoice, transitioning from a valid state to an invalid one, because invoices usually have a limit states that it can go to, and the transition is, again, very well defined. And the last point is, okay, we have all these things that we solved, but now we can call different functions in the wrong order that can lead to illegal state as well. So I will start with the first one. How can we avoid passing the wrong data to a function? And the customer of an invoice would probably have an address. And the address is like the combination of a city, zip code, and address line. I'll keep it simple. But nothing stops me from passing in the zip code as the city or vice versa. And I can still pass null values or string empties and so on, which will create an address that from a business perspective is not a valid address. So if you take a step back, and this is where we introduce the first concept from functional programming, is that the address is actually a composition of the smaller types, city and a zip code and address line. So I could write the code like this, where I can define a type for the city, a type for a zip code, and a type for address line. And this enforces me as a developer to pass in the correct parameters to this constructor. So that was easy. But of course, that doesn't mean that my city doesn't accept a null value or an invalid value, or the zip code as well. So probably the zip code is just a wrapper around the string to enforce some constraints. And these constraints, how can we manage them? So there are several ways we can do that. And one of the, let's say, most recommended way is to throw exceptions. And we have, like, how many of you used exceptions in code to short circuit or stop the execution of the program? Probably all developers that written some code used exceptions. Okay, but there are some problems with exceptions. Like, you throw them, and then someone else needs to catch them and treat them correctly, right? And that might be in your domain layer, or maybe who writes the domain is not aware of all these exceptions, and they bubble up into your application layer or another upper layer, and then nobody knows what exceptions are there, because like in C# at least, there is no way to document the exceptions. Like, you really need to write good documentation to express what these exceptions are, especially if you create your own one to express your domain. And compared to Java, where the method signature forced you to say what exception it was throwing, in C# it's like free will. Okay, so maybe you don't want to do that, because then you might just have exceptions thrown around from your domain everywhere and nobody handles them. The other approach might be to use try parse, and this is very similar. The approach that I took is very similar to what you see in the system types, like you have int or decimal, parse, try parse, and so on. But there are some disadvantages of using try parse as well. Like, how do you express what happened if the parse failed? Because there is no error there. It's just a Boolean flag that says that the parse failed. And then what happens if the parse failed? Would you return a null zip code? What is a good default value there? Because the consumer of this code will need to use that object, which in this case is nullable, And they would probably don't want a nullable object there. They would like a zip code that they can use to create the address. So, with this option, you are not throwing exceptions, but you might end up with a lot of if statements. And just think about the cyclomatic complexity of your code if you get three if statements to just create an object. It's like, you probably don't want to do that, right? Okay, so this is where the need comes to be able to represent a result as a successful result or an erroneous result. And how many of you are familiar with functional programming? Okay, so good audience as well. Nice. So we start to use the polymorphic type from language extensions in our C# programs, where we have the capability of expressing a result as a successful or erroneous result. And the construct that we used is from language extensions, the either left or right, where left is showing an unhandled result and right is showing a successful result. And as an example, if you pass into the parse method the Timisoara zip code, then you'd get a successful result. If I'm passing a UK zip code, I might get an unhandled result because my application is written to work in Romania. Cool. If you're not familiar with language extensions, but you are familiar with C#, you can think about either like a tuple that has left or right. So not both of them, only one. And this is the other concept that it's widely used in functional programming, where types can be polymorphic types where you have only one of them at a time. So you might have a success or a failure, but not both of them in the same time. So if we rewrite our code, the code would look like this. We would get all the benefits from exceptions where you can be very specific of what is happening. You can return a validation error, and then you can put a message of why the parse failed. It will not bubble up. And it's very well documented and expressive, because whoever uses this parse method will need to handle both scenarios. If it failed, they will need to write some code to handle that failure. So they don't need to guess what exception is thrown, or they don't need to have if-else's. They will need to treat those two results, if it's a successful or a failed result. But if you're not familiar with language extensions, how would you use this code then? How would you create a city, a zip code, or an address line that then you can use to create the address object? So ideally, what we want to achieve is basically call this parse method success in succession, and then if we have any failure, we short circuit the execution of our code and we just return the validation error. So it's like a chain of operations that we want to call one after another. If we use the traditional object-oriented code, the code will look like a chain of if statements. And then you already have a cyclomatic complexity of 3 here by just writing this. But you say, okay, I don't want to use nested ifs because they just make the code hard to read, or you can revert the if, but it's still the same. And still, just to create the address object, you still need to write all this code, which is, again, not what we'd like to do, right? And it's not bringing a good developer experience. This is just creating a simple address object. It should be very simple. Okay, so in comparison, by using the either construct, we can use link-you-like code where you can query those methods like from city in city.parse, zip code parse, and so on. And if any of those parse method fails, the following code is not executed, and the result object would get the validation error. If all of them are successful, then you will be able to create the address object. And you don't need to limit to the address object. You can use this to chain to create the customer then, or the entire invoice, by just chaining other operations. So by using custom types that we've defined, we were able to also prevent constructing objects that are not meeting our business needs or business domain rules, like zip codes need to follow a certain pattern, or address line maybe have some constraint as well. But we also can force or can prevent calling functions with data that is erroneous, because when we initialize our types or when we create our objects, they would actually have valid data in them. And if they don't have valid data, we don't get that entity. We actually get something else that would indicate what the error was. Okay, so illegal state transitions. How can we prevent illegal state transition? So one of the ways is to not allow the object to change. So if you create a valid object, then you cannot change it, then you can't get to an illegal state, right? So that's immutability, and that's a concept that, again, exists in F#. It was imported in C# as well. In C# 9, we had records types introduced, which actually supports immutability by positional properties or general standard property syntax. Also, they implement value equality, so you can have different entities that are equal if their properties are equal. It's not checking for reference equality. It also introduced non-destructive mutation, where you can create a new entity based on an existing one using the with operator. So it's easy to create another entity object with the same property values and just change some of them that you need. And it also has built-in formatting, so when you do to string, it will just get you the property serialized as a JSON, so it's very easy to see what the object has. If we go back to our invoice, you know we have invoice lines, or so we have collections, and usually in any object that you try to, any entity that you try to model, you would probably have collections. And do we have support in C# for this? Well, we have immutable list who uses C#, but those will not implement sequence equality. There are some extensions that implement them, but if you really want to have an immutable object that you can use value equality on it, you would need to provide some custom implementation that overrides the equals method to use sequence equality. Okay, but going back to our invoice is not a value object that doesn't change. You know, it has different states, and then we need to prevent transitioning from one state to another into an illegal one. So let's think about, let's say I'm a school employer that manages the supplies for that school, and September comes and I need to make sure that the school has paper and books and pencils and so on. So as an employee, I create the invoice request, I send it to the school director that needs to approve that, make sure that we have the budget, that I'm trying to reach out to the correct supplier and so on. And after the invoice is approved, then I can contact the supplier, create the invoice request, I can get the invoice, introduce it to the system, and pay the invoice. So you can see that in time, the invoice, my invoice instance will transition from different states, and we need to make sure that those transitions are valid. So I cannot jump from a validated invoice to a paid invoice. I need to go through all the states that my application requires. So how can we achieve that? And how can we model that using a domain-driven design approach? So how can we represent that state in our invoice entity? If initially, in my initial model, I was using an enum. So you can use enums or flags. How many of you used flags in your classes? Yeah, exactly. So you can use flags and have is valid flag, is paid flag, is approved flag, right? What about all the other properties? Do they make sense? Like approver name, if the invoice is not approved. Is it okay to have approver name? Or if the invoice is not paid, does it make sense to have payment details on that? Probably not. You can use the enum, which I used initially. So that would just reduce the number of flags and convert them to one property that has the state. Probably in that case, you won't be able to have like is valid and is paid both true, but is approved not. So you would need to have just one state. But still, you would still have all these same issues that you had with the flags, like additional properties that you don't need, or the possibility of transitioning from one state to another without nothing preventing us from doing that. So the polymorphic types, the either from functional programming, we've used the same approach to define the different states that an invoice can have by defining the type for that state. So you might have a valid invoice or an approved invoice or a paid invoice as a type. And then you can define the properties that make sense for that state in those types. And you don't leak those properties in other types as you would in the previous examples. But this has another challenge, because now we have all these different types. What make them, or how can I get to a single entity from all these different types? And as either, we can use the OR composition, where we can enforce that an invoice might be one of those types, an invalid or a valid or an approved or a paid invoice, but just one. In F# in functional programming, you have this concept of discriminated unions, where you define exactly what I've showed you there, but in C# you don't. So to achieve that, we had to build something of our own. And there is a request, I think, for Microsoft from 2020, from what I've seen, to bring enum classes, which should implement something like this, but it's not available yet. So what we did, so we had one of our colleagues, Cosmin, that implemented the choice attribute, which we used to annotate a partial class. And then during the build time, we were generating code that would handle all these, that would write the switch statement cases for all the different types that we have. So then we can enforce the developer, when using these types, to treat all the possible scenarios. And the developer will need to write something like this. Basically, you start for instance, you want to pay an invoice, you start for an approved invoice, you have the payment details, you run your business logic to validate that the payment details are correct, that the sum, the balances are okay, and everything else. And at the end of your business logic, you would be able to do a match on the invoice, the resulted invoice, and check to see if it's a paid one or not. If it's not a paid one, then something went wrong, and the developer will need to treat that scenario and give a proper functionality to handle that. If it's a paid invoice, then your transition was successful, and then you can move on and continue with your operations. So I've covered the types, and now I'll give the word to my colleague Danny to talk about the behaviors from the business logic.
Of course, we all know that domain-driven design is not only about data modeling. It's more than that. So what Fedor showed you here is how we can create types in order to restrict the options for developers, to make sure that we don't generate invalid states and so on. But we also need to think about how we build behavior now, right? Because we want to make the domain complete. So behavior in a domain is usually where the difficulty lies, and this is the most difficult part of a domain because of the complexity we have there. And in order to deal with that complexity, we usually use abstraction and modularization because we want to control that complexity. So in our case, the abstraction is that we try to break the domain into workflows which are further broken into operations that are then chained together in order to get the business process implemented that we need. So as you can see on this diagram, usually the workflow starts with some external input. We have to parse that input, we have to transform it and basically create an entity in an initial state, as Fedor showed you. In addition to that input, normally we have additional information in the database that relates to that input, and we have to look then in the database to bring the context for this operation. So we are loading also that context, and then once we have those two pieces of information, we can start calling the business rules, which are, as I said, broken into several smaller operations. So if you want to compare this to familiar notions, this is very similar to function composition from mathematics. So in the end, we look at the workflow as a function, which is nothing more than a composition between operations of that workflow. Because we are applying this in C#, we are using an abstract class to represent in general what the workflow is. And you see that we have some generic types in order to represent inputs and outputs and the context. We know that the workflow is supposed to go to the data store, so obviously we need a repository at least to load the context and to save back the result once we have finished the operation. And we also need a way to map from the result entity into an event that tells us this invoice was created or invoice creation failed with a validation error or something like that. And then we have the most important part of the workflow where we have to combine things together. And here again we have a problem of combining functions. We have at least 3 functions that we need to combine. One is reading the context from the database, which obviously can fail, right? Databases can be unavailable sometimes. So if database is not available, I might retry a few times, but if still fails, then I will have to fail the workflow. I have to stop there. If I get the context from the database, then it means I can continue, so I can start invoking the business domain. That business domain again can produce something successful or can return back a validation error, which means that again I have to stop. I cannot save in the database something that is not valid from the domain point of view. And if everything was good, then we get to the end where we write back to the data store the new state of our entity. And this will conclude our workflow because we can have either a successful result or a failure. So here again we are making use of language extension in order to achieve this composition and make things a bit easier to read. So it's very simple to look at this code and read through it, and you will see that we actually call those 3 functions one after another. And knowing the semantic from language extension that the next function will not be called if there is an error, then things should be pretty clear. And another thing that you can notice here is that we try to bring I/O operations at the edges. So we don't want to mix domain with the I/O operation. So that's why we are loading the context at the beginning and saving at the end. And in the middle we have our logic that should be as pure as it can get. And finally, we still have to deal with the exceptions, but we deal with them and the errors at the end, right? So it's that mapping part where I need to look, okay, now what do I have? Do I have an error? Do I have an exception? Or do I have a valid response? And based on that, I can generate the proper event that will tell the caller what happened. The invoice was created, or on the contrary, the invoice was not created and maybe there is an error. In order to represent the operations or the core of the domain, we have this abstract method that needs to be implemented, which gets as an input an entity in the initial state and the context, and then gives us back either an error, because we said already that domain can have validation errors, or a new valid state for that entity. And in order to implement this business logic, because it will be very hard to have everything in a workflow in a single function, and I think all of us have to deal with historical or legacy systems that are monolithic and have big functions that could span quite a few lines of code, maybe hundreds, maybe thousands of lines of code. I've seen even that. In order to avoid that, next we are going to focus on further breaking this workflow into smaller functions, which each of them deal with a specific concept of the domain. And these smaller functions follow the same signature. So they receive an input, an entity in a given state, a context that is relevant for that operation, and will give us back another state of that entity. So this is how we can transition through this operation. We can transition from one state to another. And this makes sense because this is the business domain, and in order to be able to transition, we need to apply the business rules in here. In terms of C# implementation, the operation is nothing more than, again, a class, an abstract class that has a single method, because, as we saw, we are looking at these operations as functions. So here we have an example of an invoice operation that only accepts unvalidated invoices. And the purpose of this operation or the meaning of the operation is that it has to calculate the gross and the net amount based on the VAT. In order to calculate and in order to produce the next state of the invoice, we are not mutating the object that we receive. So we are here using the record type in C# and the with operator in order to create another state which represent the transition. Because our operations contains the business domain, of course, in terms of unit testing, we want to cover these operations very well in terms of code coverage, because this is where the interesting things happens. Everything else is infrastructure, are things that glue things together, but here is where we have the business domain. So we want to keep, in order to encourage developer to write unit tests, we want to keep this as simple as possible. So we try to adhere as much as possible to the principle that we have given inputs and expected outputs. So here is an example of such a test. You can see that the setup or the arrange phase of my test is very simple. I don't need complex mocking, and in a lot of systems I work, one of the main reasons why people didn't write unit tests is that they had to mock a lot of stuff, and if you have to do that, then something is wrong. In our case, because the operations are small and most of the time are not dealing with infrastructure, there should be almost nothing. A few, maybe sometimes that you could have one or two things to mock, but not much than that. Calling or acting on the object, it's again simple. You just need to call a function. You pass in the inputs, which will be the entity state and the context, and you get back the next transition of that entity. And finally, you have to interpret the result and see, verify that you have the expected outcome. Now, it's good that we try to break functions into smaller pieces, because you can focus on a very simple thing at a time, which makes things manageable. And this is how I said we are going to manage complexity. But now the problem is how we compose them back together into something that is bigger, because the workflow is not a function, right? It's more than that. It's not a simple function. So what we need to do is to go back to the beginning, where we said that we have the workflow as a chain of operations, and we need to think how we can combine those into something that can actually work. And the problem we have here is what you see there on the slide, the fact that an operation can return not quite what other operations might have expect. So for example, validate invoice can give me invalid invoice or valid invoice or validated invoice. But the next operation in line is post invoice, and this post invoice can only work with validated invoice. So what do I do about this, right? It's not simple. I have two possible choices, but the next operation only accepts one. So normally I would use an if statement in order to break the code there and branch into two different paths. But we don't want to avoid that in order to keep things simple. So what we want to do is to allow the chain to be called, and if you don't have a valid state for the next operation, we want to bypass it and go to the next step in the line. So again, this is very similar to what we saw in language extension and the composition of the polymorphic types there, the either one. Just that we don't want to break necessarily after the first error in this case. We might want to allow the workflow to run, because there might be valid cases where you want to skip a step or something like that. So in order to make this easy for developers, we are using a Fluent API approach here. And we have this idea of a method or a function that binds things together and is responsible to transform the inputs, the outputs from one step, and so that they match the input for the next step in the line. So the runIf statement, runIf function has two functionalities here. One is to resolve the operation, and resolving the operation can be in some cases just invoking the constructor, or we might use the IOC container that we already have if we have some dependencies to resolve. And The second one is to call the operation if the state of the object, of the entity, matches the expected input. And of course, at the end, we have to look at the result and see if our workflow ran correctly, and we can tell that based on the state we are in, because if this is the create invoice workflow, then we expect to be in a state something like invoice created. If you are in state invoice invalid, then obviously the workflow didn't succeed. And if you look now into the invoice invalid, you'll find details about the error in there, because the state of that invalid invoice will give us information about validation error that prevented the workflow from completing successfully. So we can infer the outcome of the workflow looking at those resulted types. That being said, the last few slides we have presented, both me and Fedo, covered the problem with the transition of states. So first of all, we try to model the states as different types so that we can actually restrict the functions you can call based on the type. So you cannot call the post function unless you have a valid invoice. And also, the transition of the states can only happen in the operations so that we can control them. Okay? And the last part that is left there is how do we call these workflows from an API, for example. And here, again, we want to apply 3 simple steps. So we want first to take the input that we got from outside, which is usually untrusted, right? So we need to parse it using what Fedo showed you, those approaches, in order to obtain an initial state of the entity. In addition to that, once we have the entity, we can now start calling our workflow. And at the end, we have to do the opposite, right? We have to take the event that we got back and transform it into something that external caller can understand. So again, the code here is very simple. And the first line, the first thing we try to do is to, as I said, to map the input to something that we can trust, okay? Then, once we have the initial state, we start the workflow, which will chain all the operations until we get the outcome. And here again, we are making use of the match operation in order to interpret the result. And for example, if the result is invoice created, we know to return 201 status code back. If we had invoice creation failed, then we know that the input we got was incorrect, which means bad request, so we return 400. And finally, if there was an exception or something unexpected, we are going to return 500 error. To conclude this presentation, there are a few things that we try to show here. So first of all, we have tried to use types in order to model domain constraints and to limit the invalid options. We have made use of functional programming in order to make some of the things easier, especially around function composition and how we restrict user from modifying objects directly. So we have used immutable recurse choice types. We have broken the workflows as functions, and we are usually trying to avoid exceptions, and usually we prefer to return results so that outcome is always clear to the developer that uses our APIs. There are a few principles that we try to adhere to, and among those we have this idea of model the domain as a set of workflows. Then we try to always bring the I/O operations to the edges. Again, it's something that many people do in the industry today. And we try to separate domain model from API model and database model, because normally those 3 things, although they are very similar, in the end you realize that they have different requirements. They will cause issues if you try to mix them together. There are a few references that I would strongly recommend checking if you are interested into our presentation. So first of all is this book, Domain-Driven Design Made Functional, by Scott Blushing. A lot of the concepts here are taken from that book. The book itself presents these concepts in the F# world, And what we did here, we took those and applied them, but in C#, because this is the language of choice for our company. There is also a Git repository that you can use if you want to have a look at our examples, and a few more links there, among which language extension library that again brings functional programming concepts into C# and the C# choices that Cosmin built in order to make possible using polymorphic types in C#. That being said, this concludes our presentation. Thank you.